Hey, thanks, Johanna. Hello and good morning, everybody. Just to introduce myself, I'm Robert Sigmund, working for GAF in Munich in its development unit and dealing mainly with SAR interferometry and SAR application development. In today's webinar, we are focusing on applications of the European ground motion service related to the climate change adaptation. And before starting with the presentation, I'd just like to thank the team, the DLR, GAF, and the complete consortium for this brilliant work that has been achieved yet. But let's get into it. So this is the fourth of a series of 5 webinars on EGMS. The first one are already available on the EGMS website. So the remaining webinar will focus basically on urban areas and infrastructure. So be sure to attend, and also just to state, I will not talk too much about the infrastructure and urban topics in the climate change adaptation. So please join the next webinar that will elaborate that topic further. So also for you to note, besides the webinar dates, is the publication of the next EGMS product update. This will be available in September this year. But now, for today's webinar, I will just give a short overview of EGMS. So in particular, what is it, what we are talking about, what's the underlying technology, a brief overview on the EGMS product, and the main topic itself, the use of the EGMS data for climate change adaptation. So coming to the first question, what is EGMS? The European Ground Motion Service, or EGMS, is a recent addition to the Copernicus Land Monitoring Service. The EGMS products are generated from Sentinel-1 data, the radar satellite mission of Europe's Copernicus program. So it is a pan-European service covering Europe, including the Azores and Canary Islands, plus the French overseas departments. The service provides continental scale measurements of ground motion in a high density set of points comprising the mean deformation and associated deformation time series. And regarding the temporal coverage, the update currently available on the website covers a time period of 7 years from 2015 to 2021. And also please note now that until late 2021, the 2 operational satellites of Sentinel-1 guaranteed a 6 days revisit time, while from early 2022 onwards, the revisit decreased to 12 days since one of the satellites faced a technical defect and is out of operation since then. But now, what do we actually measure with EGMS or in EGMS? The EGMS products provide measurements of the millimetric scale motion of ground-based features that provide a reliable and stable reflection of the radar signal over time. These ground-based features may be natural, such as the bare rocks, or man-made, such as buildings and other types of artifacts. EGMS itself provides data for more than 10 billion measurement points, or MPs, each one attributed with a series of parameters like the mean velocity, the associated time series, and seasonal deformation amplitudes. The displacement itself we measure can be caused by various ground motion phenomena like the land subsidence or the consolidation of sediments, landslide, groundwater withdrawal, and so forth. But we will get to that later. Just brief how to access the EGMS. So it's usually done via the EGMS Explorer tool, what's accessible via your browser. It allows you to view, analyze, and download the EGMS data. Here on the top right corner of EGMS, there is a toolbar that provides a number of functions like point and click time series analysis, plotting, and stuff like that. And please note that for data download for registered users, that this download is performed on a tile basis, not on an area basis. So meaning you receive data blocks that intersect your search area. But this issue will potentially be solved in the near future. Actually, no registration is required to use the Explorer for visualization. The download of data from the archive, however, does require the registration using the EU login. And here you can either create a new account or log in with an existing EU login account. But let's now take a quick journey through the technology that we're using in EGMS. And also just to note, this is a very basic and brief review. You'll find detailed description in the documentation that's available on the service website, and respective in the document, the algorithms, a theoretical basis document. So the EGMS utilizes the data of the Sentinel-1 mission. And this mission initially consisted of 2 identical radar satellites in a near polar orbit, 180 degrees apart. The radar satellites themselves are active systems emitting pulses of electromagnetic radiation and then record the strength of the return, the time delay, and the phase. The EGMS products are generated from hundreds of SAR image acquisitions over the same locations across the EUROM territory, meaning we are dealing with a real huge volume of data there to provide the service. Essentially, to know is just the imaging geometry, because we are when we are discussing things, we need to regard the terminology. We need to keep in mind that a radar is a ranging technology. So for image formation, the satellite needs to take a look aside. Therefore, we can only measure the projection of relative displacements along the vector between the satellite and the ground, which we call the line of sight, or in short, the LOS. The analysis of the radar data is done by using persistent scatter interferometry, which represents a multi-temporal interferometric technique. And the EGMS data processing utilizes, therefore, stacks of Sentinel-1 radar imagery taken over the same location. The displacement of an object on the ground plus the changes in the atmospheric conditions between 2 successive images are measured then by the phase difference of the returning signal. The atmospheric contribution to the interferometric phase is estimated and minimized over the large stacks of images. And EGMS therefore utilizes this multi-temporal interferometric technique, and predominantly the persistent scatter interferometry. That means the spectral stability throughout the time series is prerequisite. So therefore, the method reduces to permanent scatter point measurements, and their density is high over built environment and low over rural vegetated areas where the signal decorrelates between the satellite acquisitions. Then the displacement and the resulting velocities are determined in line of sight geometry, as we mentioned by the side-looking radar, meaning we find motion towards or away from the satellite when we apply this technique. But we can't end the technical part without summarizing the main limitations of the method, such as the MP density and distribution. So PSI, or the persistent scatter interferometry, relies on ground features being radiometrically stable over time. Therefore, the MP density varies with the surface characteristics. The 3D positioning. So here, the PSI measures displacement within millimetric accuracy, while the 3D positioning of points is of meter scale precision. We have another issue, the spatial resolution, because it's been asked quite often. So the Sentinel-1 SLCs that are fed in the process, these products provide a ground resolution of approximately 20 to 5 meters, limiting the resolution of EGMS basic products and the MPs to 1 resolution cell. So it should be noted that the spatial resolution in our terminology corresponds to the ground resolution cell. So meaning 20 to 5 meters for the basics, or the grid cell for 100 per 100 meters for the ortho products. Also not to forget is the north-south component of the displacement. So, and due to the east and west look direction of the satellite and its corresponding ascending and descending orbits, the north-south component of a displacement is underrepresented here. So we can't actually measure this component, always for you to remember. But for more information, please have a look at the product user manual. Everything's available directly on the website. But before we're coming to practical aspects of EGMS, just let's switch through the list of products that we are providing in the service. And these are basically 3 main products: the basic, the calibrated, and the ortho product. The basic product contains the initial output of the PSI processing, meaning the deformation measured along the line of sight relative to the local surrounding area. These data are available for you for download, but not visualized within the Explorer. The calibrated product contains the same content, basically, like the basic data, but reference to a GNSS-based pan-European velocity model, so that the product relates to a European geodetic reference system. The ortho product finally comprises of 2 layers generated from the calibrated ones to provide the vertical and the eastward horizontal motion. In all the products, the displacement time series revealing the deformations over time are available for each MP and in the viewer just by clicking on them. All of these products provide a set of attributes, including quality parameters, such as we can treat the temporal coherence as such a parameter, since it's a measure for the accuracy of the determination of the interferometric phase. But for an assessment itself of the quality, you can also refer to the relevant documents on the website. It's the EGMS D10.x. It's a series of documents, all dealing with the quality. But finally, just for the special case of the ortho products. The ortho data are produced on a regular grid within 200 meters spacing with a regular temporal sampling of 6 days. And for each of the grid cells, all available calibrated data are aggregated, taking into account the different line of sights to produce a separate ascending and descending displacement time series. The vertical and eastward displacement components are then estimated per grid cell. And again, it's important to note that we cannot measure the local north-south component of displacement due to the geometry of the satellite acquisitions. In our decomposition process, nevertheless, we assume that the observed north-south component is 0. And to illustrate and to move one step ahead to climate change, we have here an illustration of a calibrated and ortho products in an example area in Mals in South Tyrol in Italy. And in here we find high alpine terrain that's affected by ground deformation. It's mainly landslides or potentially rock glaciers that might be increasingly activated by receding permafrost and the precipitation. We get an indication of the true direction of the motion by using the 3D view here in the Explorer, as I visualized here in the images. In the calibrated data, visualized here, the areas of effect of ground deformation are clearly identifiable. If you just have a look here on the red or blue clusters in the image. And most of them show opposite colors in or opposite velocities in the two acquisition geometries. That's typical actually for motion with a significant horizontal component like landslides. And this expresses as well in the ortho products. And here we find significant motion in the eastward component here on the right side, and due to the steepness in the vertical one. In our case, after decomposition, we can interpret the motion straight, because in our case we see that the western slopes move more westwards and down, while the eastern ones are moving eastwards and down. So just to illustrate the use of the ortho compared to the line of sight calibrated product. But so far we are now through with the technical background, and let's get a bit more practical and talk a little bit on the use of EGMS data for climate change adaptation. But how do deformation measurement and climate change adaptation fit together actually? So I'll try to demonstrate that on some specific examples. But first of all, the EGMS products, or in general, they can be used for climate change adaptation in general for awareness, assessment, planning, and monitoring. When we're talking a bit more specific, we'll concentrate geographically on two main categories in areas affected by climate change that are represented in coastal zones, like when we are talking about vulnerability, protection, management, or inland areas, when we mainly address the changing permafrost, the precipitation, or the potential of the deformation data for hydrologic modeling. But the practical use of the deformation data in this context, what's to say about that? The EGMS deformation data, so just some statements in advance. So the deformation data, they do not directly measure climate change impacts. So in other words, it's not a measurement of water or flood height directly, or changes therein, or surface changes due to erosive effects. That's another thing. That's another topic that cannot be measured with PSI. But the data products are well suited for integrated analysis together with different data sources like in situ, especially for local assessment to determine the relative sea level rise, or potentially for detailed analysis when we're looking at specific infrastructure elements or sections inside these elements. The data products can serve as an indicator for instabilities or surface deformations due to meteorological or hydrological conditions and changes therein. So, and finally, that will be the final example. The data can also be used as a base information to be integrated into hydrological models, like the groundwater management. But first of all, the coastal zones and the main parameter, the sea level rise or the relative sea level rise. What are the European countries are confronted with? We know that the global mean sea level has risen about 21 centimeters since 1900 at an accelerating rate. And this sea level rise will affect people and assets in Europe, European coastal areas severely, especially in low-lying and densely populated regions. And the European countries face varying degrees of risk and vulnerability due to the SLR, depending on the local relative sea level rise, plus the storm surges, the recurring coastal river floods, and the existing flood defenses or the adaptation measures. And how is it distributed along the European coast? What to expect? In summary, we can just tell that an increase in absolute sea level and relative sea level in most of European coastal regions will appear or will be is to be expected, except for the northern Baltic Sea and the northern Norwegian coast. And the relative sea level rise is especially relevant for coastal protection. So that's the main parameter that we're dealing with in the coast, also along the coast. But what does that mean in terms of coastal vulnerability? First of all, the coastal vulnerability represents a complex problem to be addressed and managed on a local level. The local relative sea level rise can put at risk important critical infrastructure such bridges, roads, railways, and harbors. The population of these areas is confronted with growing risks and coastal flooding, wetland loss, shoreline retreat, and stuff like that. The environments are influenced by significant water level variation. So actually what's needed is a sustainable coastal zone management and its impact and risk assessment based on adequate information and data. But here is an example for a subsiding low elevation coastal plain that faces an increased flood risk or even increasing flood risk. The example of Sibari in southern Italy. We find that the projected trend for sea level rise is significantly high for the coast of southern Italy. And damaging flood events are well known through the past and even from history, and they are documented specifically for the archaeological site there. The ground deformation that we see in Sibari Plain results from groundwater overexploitation at nearby nautical centers, residential areas, and industrial zones, and due to the sediment consolidation processes. But problematic is an increasing risk exposure to flooding for the cultivated and inhabited areas, plus the archaeological sites there. And when we are looking at the EGMS ortho data, we measure here deformation rates of approximately minus 14 millimeters per year and a linear trend throughout the time period. And we can state that this results should be integrated into any planning process in the future. But when you're going more from extended features more to detail, we would like to show you just the potential or the rendering of small-scale objects that could be visible in our data. And here is an illustrative example that especially addresses the detectability of localized structures, like in this visualization, where we find a light railway that connects the small islands of the German Wadden Sea with the mainland here. And it's, as I mentioned, it's light and very small. But for the future, it's exemplary for maintenance work or protection of those coastal infrastructures facing the higher mean high tides and storm surges. What I'd like to show is the sensitivity of the PSI measurements even to those small scale objects. And we see that the rail track is even rendered in the EGMS 100, as in the ortho 100 meter grid. And we see additionally in sections of the railway deformation trends of up to minus 8 millimeters per year vertically. So also in the time series. This could be followed on with more detail, also just to visualize for you. It's rendered already in the 100 meter data, but for detail analysis, you would switch to the calibrated data there because we have a much higher density along the rail tracks or the infrastructure in ascending and descending geometry. Another topic, and in contrast to the former example, we have harbor infrastructures and open sea settings that require specific protection measures. since these protective elements of the infrastructure are exposed to offshore marine conditions and the mean sea level rise. So therefore, we just briefly selected Gijón Harbor in northern Spain, since we found some operations, the extension operations that had been conducted between 2005 and 2010. And here in this harbor area, and looking in the EGMS data, we see deformation rates of up to -8 millimeters per year in the recently constructed sections. So to say that we are able, or that EGMS information provides the opportunity to differentiate between stable and unstable areas in those artificial structures. So, but to move further ahead, but still worth to be discussed, but I will try to make it short. We have some specific conditions in estuaries that I like to show and like to discuss, since these specific regions are very sensitive to climate change. The mean sea level rise plus the increased intensity and the occurrence of extreme events. So things add up here. And the climate change there causes hydro and morphodynamic changes in a dramatic way, especially with the trends in atmospheric, in the rise of temperatures and precipitation, that it will increase or change the summer and winter runoff that will collide in the estuarine systems. And so therefore we see a need for action predominantly in the short and medium term with coastal engineering, but also in the long term for flood protection and risk management there. Just to raise some topics and raise these topics for discussions, I will show some examples along the Scheldt estuary in Belgium and the Netherlands, mainly for 3 specific areas, like a polder area and a area for critical infrastructure at the Doel nuclear power plant and the Antwerp port. So it's actually, so why I'm talking about that. So the estuary allocated on the alluvial plain is sinking, and that was proven by a geologic study. But nevertheless, in here are important elements like the economic engine of the port of Antwerp or the metropolitan area of Antwerp. We have the critical infrastructure along the coast, and we have coastal protection measures like here in the polder area. And when we have a look at the polder area and the dikes therein, we see just from the EGMS viewer that we find a recently established polder area there that was built probably between 2012 and 2018 with the dikes structure surrounding the central area. And in here we find in this new infrastructure deformation trends of up to 6 millimeters per year to -16 millimeters per year downwards in the author products, and also with the same characteristics and trends on a high resolution in the calibrated data. That's typical behavior, I would say, for consolidation processes here along the coastal protection infrastructure. But another topic would be, what about power plants or nuclear power plants located there on the coast of the Scheldt that might be facing a higher mean tidal height or flood risk. And when we have a look at the Doel nuclear power plant here, we see a subsiding area in the north of the power plant structure that is also mapped in the line of sight in the high resolution data there that are probably related to consolidation processes as well, like in the example shown for the dikes. So, but these are localized phenomena. It's a bit So, but coming more from the localized phenomena or the localized effects, more to an extended version of effects. Just to mention the port of Antwerp in Belgium, and why do I mention this? Since it is of special importance as an economic engine, and it's surrounded by the urbanized metropolitan area of Antwerp, and it's in the upper estuary, so still affected by the tides and the floods. And geologic studies that use PS analysis were already performed along the Scheldt Valley in the city of Antwerp, and they showed that the harbor area and the valley is characterized by negative line of sight velocities, meaning it's sinking due to human activities there, like landfills. And that's essentially a topic for the new developed structures along the harbor that are consolidating at a higher rate, like the older ones in the city center of Antwerp. That's easy to differentiate. We see in the data of the study based on Sentinel and the EGMS calibrated data, corresponding structures, corresponding velocities there, and we see that the city center, which is already consolidated, provides deformation rates of about 0, so that's stable, while the newer the structures that have recently been built, the higher the rates that they are sinking. So that's actually the message that I wanted to pass, and that the results agree well within the studies, with the results of the study. But let's leave the coast behind and go towards another topic, meaning to move towards inland areas, the Alpine region at first. And let's talk a bit about the adaptation facing or addressing the receding permafrost or the changing precipitation patterns that are affecting several areas throughout Europe, but I'll concentrate on the Alpine region, since we have a quite extensive study there, and this previous and extensive analysis in the Italian Alps here in South Tyrol show that the instabilities related to the change in precipitation and temperature are increasing, and this effects will potentially result in a higher activity of rockfalls, landslides, debris flows, or rock glaciers. So, and based on the results of the study, we compare the EGMS products in those regions with increased activity with the results of the study. And subsequently, I will just show some areas that are indicating instabilities and potentially active rock glaciers in the area west of Meran, between Flanders and Mals. So, and where do we find those active areas? So that's the valley. We have the high alpine terrain here. That is visible here in the Alpine Permafrost Index map that's provided by the University of Zurich. And here in this permafrost regions, we have the possibility, or we find the possibility for increased activities of rock glaciers in these high alpine zones. And what was also reported by the performed study. But in the EGMS ortho data, in the vertical and horizontal components visualized here in this image, we find basically that these products are usable even in high alpine terrain, and that's not that's worth to mention here, since the structures of the terrains are properly mapped in the non or less vegetated areas, so suited for to be analyzed further. And in here, in this terrain, we find localized motion that is potentially related to instabilities and are detectable in the product, and potentially are related to rock glacier or active rock glacier processes. And what we see is in the vertical component, okay, points are moving down, but in the horizontal component, we see the characteristic that I described already before in the technical section, that these characteristics are directly interpretable in the horizontal components, meaning we have this westward or eastward motion, especially in the areas that are located along the slopes. And for further studies, one would even concentrate on the high resolution data, the line of sight calibrated data visualized here, but they need to be interpreted carefully with in situ data, considering topography, but best suited for further analysis. But finally, my real final example, we're moving just from the high alpine permafrost to the groundwater management, which is a drastic topic at the moment. And just to state that the climate change is expected to increase the demand of water for irrigation in Europe drastically. And the recent developments show now a precarious situation on of the groundwater table in southern Europe, with an increasing water stress that's affecting the European territory and the people already. So, and the droughts cause economic damages and additionally unquantified damage to ecosystems as well. So deformation, this is a drastic topic, but we see that deformation due to groundwater abstraction is visible in EGMS products. And just to show you how it could be used. So I included the example of the Prato Pistoia basin in Italy here. Here is an example for the relation of aquifer situation and ground displacement. So the groundwater withdrawal can lead to a consolidation and therefore the deformation effects on the surface. And we know that especially related to climate change, we will face usage conflicts of fresh water, and that's foreseeable. And so therefore the groundwater management becomes fundamental in the near future. And so by integrating geologic and hydrologic information, the deformation measurement is able to provide an indication of the changes in the groundwater situation, or could even serve as a base for hydrologic modeling. And this study that was performed, this study provides an approach to model the complex relationship between the aquifer condition and the ground displacement. In our case of the groundwater abstraction here in near Pistoia, we see that we would concentrate again on the vertical motion here in the data that's here visualized for the EGMS author products. We detect in the center, in the city center, a motion of about 7 millimeters per year down, also meaning minus 7 millimeters per year, while the agricultural zone where the plant nurseries are distributed sink at about minus 13 millimeters per year. And that's quite significant and match well with the results of the study that had been performed. The study that used those data to model the situation or the conditions of the aquifer beneath the surface. So this is to show how the data or the deformation measurement could be used or are beneficial to be used for those questions or for those problems. But let's come to an end, and I hope that I could give you, at least a short but comprehensive overview on how the EGMS data could be used for the climate adaptation analysis, hopefully. But anyway, there is still a lot of documentation available on the EGMS website. So feel free also, as not only to source the documentation, but also to contact us via our EGMS help desk. We will try to provide support and answer any of your questions, and also try to improve our service further via this channel. So to contact the help desk, please don't hesitate to click the help button. And for practical purposes, if you're thinking or face problems in a certain area, please be aware that you can include the link to this area in an email, send it to us and point it towards the location of your problem and in the data. So the very last slide, so just pointing you to the upcoming webinars. We have one more upcoming webinar. The registration is free and will be open a month in advance. So please be sure to keep an eye on the EGMS website. And so I will just leave the floor. I will just thank you now for being patient, and thanks for your attention. I will leave the floor for questions and answers.